Next we go to a different topic, what is harmonic function. Okay, so this is a topic in analysis. This course is aiming to discuss probabilistic method in solving problems in analysis, including differential equations. So here we are going to discuss few such properties of harmonic functions, which are subtopics of analysis, and we are going to explore those things using Brownian motion here. So we first define what do we mean by a harmonic function. Let D be an open subset of Euclidean space, of D-dimensional Euclidean space Rd. Let U be a function from D to R. So D is open domain and U is a real valued function defined on D. We call this function U harmonic in D if U is twice continuously differentiable on the domain D. Furthermore, its Laplacian value is 0 everywhere in D. Okay. So, what is Laplacian? Laplacian is that second order derivative, correct. If it is coming from one dimension space to R, then we just say d2u dx2, but it is say two dimensional space, then we say del 2 del x square plus del 2 del y square of u is equal to 0. Okay. So, similarly for higher dimension one gets the form of the Laplacian. Now, we consider a stopping time tau d. Tau d is defined to be the exit time by the Brownian motion from the domain D. Okay. So, this is a stopping time. Why? Because Brownian motion is FT adapted, and exit time of FT adapted process is a stopping time with respect to the same filtration FT. Now, we consider the closure of D, we write down as D closure, and that is equal to D union the boundary of D. So, that is the boundary we have. Okay. D closure is equal to D union boundary of D. For each bounded domain D, probability that the stopping time is finite is equal to 1, does not matter where the Brownian motion starts. Okay. So, if consider the Brownian motion starts from a point which is outside the domain, then of course tau d would be 0 because it is already outside.
So, is it here the D is bounded domain or?
We have started with any open subset, need not be even connected component,
No,
but here bounded D. Okay. So, when we assume that it is bounded D, then if x is outside the D, then of course tau d is 0, but if x is inside D, Brownian motion hits the boundary of D and exits D, okay, in a finite time with probability 1. Okay. So, it remains in the domain D forever with probability 0. So, it would hit and exit in finite time. So, or in other words, we write down that tau d is finite with probability 1. Now, we recall certain formulae. Okay. So, here notation B subscript r is denoting the open ball centered at 0 with radius r. This is the definition, correct. Mod x is less than r when x is in Rt. The volume of Br we write down as Vr, okay, V subscript r, and that is 2 by d pi to the power of d by 2 gamma of d by 2 r to the power d. A very simple exercise that you cross verify for say d is equal to 1 case. Okay. D is equal to 1 case, it will be pi to the power half, but below is gamma half. Gamma half is also pi to the power half. So, this gamma and this numerator and denominator would cancel each other, and r to the power of 1 would appear and d 1. So, 2 times r. Okay. So, that is the interval length, correct. So, when you have r distance left, r distance right, then the total length is 2 times r. So, next we go to the surface area SR. The surface area SR is obtained by taking partial derivative of V with respect to R, correct, because that is how you get, okay. You integrate surface area with respect to R and you get the total volume, or in other words, to get SR you take partial derivative of V with respect to R, okay. And that is, if you do that, it is trivial to check that you are going to get d by r VR, okay. Next we introduce a measure mu subscript r, we call mu r, a probability measure on the boundary of the ball beer, okay. So that is given by mu r of A, where A is any Borel subset of the boundary of beer. So what does it mean? That you have a Borel subset of RT and you intersect with the boundary of BR, then what is left, that you call the Borel subset of BR, okay, del BR. So the boundary of BR, okay. So you consider any such Borel subset of del BR and then you define the mu r measure of the set A in the following manner. This is the probability, the P is missing, probability that W tau BR, what is that? That is the Brownian motion value at time when the Brownian motion touches the boundary. So tau BR is actually the exit time of BR ball. So at the time of exit time, so the Brownian motion should be found at the boundary itself, okay. So we are going to compute the probability. If you compute the probability that this point of Brownian motion is found in the set A, okay, what is the probability that this point of Brownian motion, which can exit BR in various different parts of the boundary of the ball, but it is found in the set A, okay. So that probability is going to give a number, and that number we are going to call mu r of A, so measure of the set A, okay. So that is the definition of mu r. Now ball is symmetric around origin, Brownian motion is also symmetric. So this measure is also symmetric in the sense that, okay, if you have A here and if you rotate A around the origin, and the measure would remain the same, measure is not going to change. Due to the rotational invariance of Brownian motion, as I have explained, that one would obtain that the function f(x), if we evaluate the function, the integration of f, okay, on the whole set BR, so whole interior and boundary everything BR. So whatever we are going to get is exactly same as if we take levels of spheres starting from 0 to radius r of various different radius rho is starting from 0 to r. So that then we are going to get the spheres, del BR are the spheres, and then if we are integrating on the sphere using the measure on the sphere, that is mu rho, and then that thing whatever number we are going to get, that we are again integrating from 0 to r as S rho d rho. What is S rho? S rho is the measure of the area measure of the sphere. Why do we need to do S rho? Because mu is normalized, it is probability measure, okay. It as the surface is growing, okay, the measure of the surface, okay, would be S rho times mu rho, because mu rho is just a fraction, is just a probability. So mu rho dx S rho times d rho integration 0 to r. So that is the identity. And now if you replace f by 1, okay, there is a special case f by 1, then left hand side you are going to get the volume VR, and here you are going to get f is 1, this is a probability measure, the whole integration is 1. So you are going to get 0 to r S rho d rho, correct. So we are cross verifying, okay, see, you can actually retrieve the this thing from here. So, this is generalization of the above. Okay, we are going to use these notations and these relations in the next slide. Now, we introduce a notation or a terminology which is called mean value property. So, let U be a function from the open domain D to R. We call U to have mean value property if for every point A in D and R positive, such that we can actually include a ball of radius R is small enough such that A plus BR bar. So, this is nothing but ball of radius R centered around A is inside the domain D. Okay. So, we can always do that. So, A plus BR, a open ball which is subset of D, if its closure is not in subset of D, we can take the half of the radius of, and then we can assure that that would be in the open domain of D. Okay. So, we can always obtain such R positive. One has that U of A, okay, is equal to integration of U of A plus x mu R dx, where integration is over the boundary of the ball. So, this is like average surface area measure, correct? U of A plus x mu R dx over del BR. Then we call that U is having mean value property. Okay. So, not every function satisfy this property. This is like saying that if my point A is considered and then we consider a ball around A, and then whatever the average value, because this is average value, right, A plus x on the sphere around A. Okay. So, point A is there, but you are considering a sphere. On the sphere you are evaluating the function U and finding out its average, correct, and that is exactly same as U of A. This is very special rigid property, correct. Not every function has this property. So, if a function has this property, then we call that function to have mean value property. Mean value in the sense the average value. Okay. So, does not matter whatever sphere you take, its average value is assumed by the function at the center of the ball. So, under that assumption, for that class of functions, we have following relations. So, let us see what is this relation. U of A can be written as 1 over V R. So, what is this? Just I have written U of A, but then S rho d rho integration 0 to R is V R. So, V R numerator and V R in the denominator would cancel each other. So, it will be U of A. So, U of A is written as U of A multiplied with S rho d rho integration 0 to R, and denominator is V R. Then that is equal to 1 over V R integration 0 to R. Here we are going to use this formula, okay, this property of U A. So, U A is replaced by U of A plus x integration with respect to mu rho on the sphere of radius rho and S rho d rho. Okay. So, here we have obtained exactly what we have seen this relation here. Okay. So, that type of things. So, U of A plus x mu rho dx S rho d rho, this thing. So, this part would be same as U of A plus x integration on the whole ball of radius R. Okay. So, that is this thing. Okay. So, U of A can be written as 1 over V R integration of U of A plus x dx on the ball B R. Next, if U is harmonic in D, that means U is twice continuously differentiable and Laplacian of U is 0, then we are going to show that U has mean value property. For proving, let us consider a point A in D, okay, and R positive such that A plus BR closure is subset of D. To prove mean value property, this is the way to do, correct, because for every point A we are going to show that, okay, that mean value property is true. Remember that this statement itself is a statement in analysis, correct. It involves no probability, because it says U is harmonic in D, that means it has some analytical property, and we want to prove that U has MVP, mean value property, that is also an analytical property. Okay. One can say, okay, that in mean value property it involves mu r which came from Brownian motion, but actually we know that mu r, this measure is nothing but normalized surface area measure, correct. So this is like an analytical property. So we are going to prove this statement, which is a topic of analysis, using the stochastic process theory, whatever we have learned till now. Okay, so this I have done. I have discussed A is a point we choose and R is the radius we choose, such that it can be inscribed inside D. So let Y be a process which is starting from A, because Brownian motion starts from 0. So this starts from A. So it is translated Brownian motion, and then tau is the stopping time when this this process Y leaves the ball. So it starts with the center A, and then at some time when it leaves, we call that tau time, exit time from the ball by the process Y. Now, as we have already discussed before, that probably tau is finite is 1, because it is a bounded ball. Then expectation of tau minimum t, okay. So this is finite to Y, because tau minimum t is anyway bounded random variable, and expectation under probability measure is a finite measure. So this integration is finite. So expectation of this is finite. Again, you can be extended to a twice differentiable function with compact support, okay, beyond that ball. We can do that, correct, because when you consider u on the domain D, from that we have shifted our concentration only at point A and the ball around A, okay, of radius r. And then by not changing the function inside the ball, okay, closed ball, we can extend, okay, we can modify outside that to make that as a continuously twice differentiable function with compact support. Okay, we can do that. Thus, we can apply the relation what we have earlier discussed in the beginning, that this is the end of the proof, that f of this thing, correct. So here f was Cc to Rn. Okay, so you can use this result. So we are going to use this result now. Okay, so remember here. So here y tau is like this, but for our application here x is A, this is u is 0, and v is just identity matrix. So all these assumptions, whatever is written here, everything will be satisfied. Okay, so we consider this, we apply that theorem. So we get expectation of u of this process is equal to u of A plus expectation of the this second derivative term. First derivative term does not appear because that is taken dot product with the drift term u. Here u is 0, so that does not appear here. So here 0 to tau minimum t appears, half times Laplacian of u of YAS ds. So after obtaining this, we now apply use the fact that u is harmonic, because it started with u is harmonic. Since harmonic, that means Laplacian of u is 0. Okay, Laplacian of u is 0. So here this part would be 0. So we are going to get this expectation is equal to UA. So expectation of this is equal to this for all t positive. Okay. So now u of A can be written as, here capital T is there, correct. We have to get rid of capital T, because I should only deal with tau. Okay. So we take limit t tends to infinity of this thing. Okay. So we use Dominator convergence theorem DCT. Here C looks like a subset, but it is DCT. Okay. Using Dominator convergence theorem, this is expectation of u of YA. So this is typo, it should be just tau, there is no minimum t. This is going to converge here as this this random variable is converging to this as capital T tends to infinity almost surely, and u is continuous and bounded on the set B R closure. So we can use the Dominator convergence theorem here. So this term, this expectation, we are now writing here. So here there is a typo, it should be just y superscript a subscript tau, there is no capital T, is equal to integration on the surface of the ball. So, this is basically sphere of u of, why is it so? Because at tau, I mean the process y is on the boundary, because tau is the exit time. At that exit time, y must be on the boundary of the ball of radius r. Okay. So, a plus x, and then for this expectation we know that okay, mu r by definition is the probability that it is found on that set, okay, on the boundary. So, this expectation can be computed using that u of a plus x mu r dx. It is coming directly because of the definition of y is x plus w, correct, and the probably the w touches some points, okay, that is giving the mu r measure. So, it is this u of a plus x mu r dx. Okay, that is it. So, this saying that okay, for does not matter what a point we choose, all the time whatever r positive radius we can find such that the ball is inside the domain, I would always get this relation that u of a is equal to u of a plus x mu r dx on the sphere. Therefore, u has mean value property. Okay, mu r is the distribution of w tau on del p r. Okay, so this. Okay, I think I would stop here. Rest I would discuss in the next